Okay, sorry about that. I forgot to put my phone on Do Not Disturb, and I got a phone call and it shut the video off. All right, so I was just finishing up this page saying that in reality, there's more going on with this beta decay situation, and the book says it doesn't want to really go into it, but when something is decaying in this beta process, the neutron turning to a proton, we have an electron emitted and then also an antineutrino emitted. And that's a pretty complicated topic that he didn't want to go into, and that really is because then you have to go into the fact of what neutrons are made of, the quarks that they think neutrons are made of, and then how when there is a change in that, how we have the W boson release, and it's just a lot. So don't worry about that. But the other thing is that you can also have this other way. You can have a proton turning into a neutron, and then so by absorbing the release of the positron and a neutrino. So smaller particles that we're talking about, all these quarks and all this stuff, they're saying created in the decay process. I'm sorry, not the quarks, but the antineutrinos and the neutrinos are something that are created in this decay process. So it is kind of complicated, but for our point, at this level, all we have to know is beta decay is the neutron's going to turn, and this beta particle is going to be spit out, and then in the end, the original sample isotope is now going to be a different type of isotope with one more proton. All right, then the last of the decay process that we needed to talk about, or the last page, is the other two. So alpha decay and gamma decay. So alpha decay, and is like I said, normally the one that you would start with, is when a radioactive isotope emits an alpha particle. Now, you probably heard of this before, alpha particle, and you might, if you haven't studied, you might not know what they were talking about. But it's basically the small nucleus that gets spit out by this isotope. So this, whatever this radioactive isotope is still trying, just like with the beta, still trying to get rid of some of its nucleus because it's unstable, it's too big, it's not balanced out. And so it'll spit out a small nucleus broken off of it that contains 2 protons and 2 neutrons. So 2 positives will be spit out and 2 neutrals will be spit out. Now, that's a lot coming off of that isotope there. It's not just one little electron. It's a whole nucleus. And it's actually a whole nucleus of what you probably already saw there, of helium, because helium is number 2, so he'd have 2 positives, he'd have his 2 neutrons, and he'd have his 2 electrons. So this is a nucleus of actually helium-4, so it's of the isotope helium-4. I should put that there. So because helium can exist in different isotopes depending on how many neutrons he has too. So, but the difference is here, the nucleus is just flying off. Not all are flying out of that isotope. We're not having the entire atom with its electrons and everything. It's just the neutrons, the 2 neutrons, and the 2 positives, or the 2 protons. And so when this happens, we're going to have a change just like we had before, but a little bit of a different change. They give us an example of polonium. And, you know, this is one of Marie Curie's discoveries, and she named that after her native country. And so she did not understand when she was working with polonium and some of the other radioactive isotopes that she found, that she was in the presence of this, what we call radioactivity, in an abundant amount. And so what was happening to her and those who worked with her is when these things fly off, whether it's beta decay or alpha decay or gamma decay, those things are flying off the atoms in the process of trying to decay to become stable. And if you are sitting next to them, they're flying into you. And so if it only happens in a small amount, it's not a big deal because we're always dealing with things flying off of atoms and hitting us, and we don't even know it's happening. Like they say, even a banana is radioactive. So depending on how much you eat, you'd have to have, I forget how many tons of bananas you'd have to eat for it to be problematic. But So, but these things are happening all the time with atoms around us. It's just, we don't even see it, and we don't see, and our bodies are made to reproduce more cells if cells do get damaged. So as long as we don't get into a situation where we're in the presence of too much flying off too fast, too much that our cells can't remake in case something did happen to one of our cells, it damaged one of our cells, like we're in the presence of a gamma decay or something like that, and that's a lot coming off, and if we have a lot of gamma going on, then we would be in more trouble. So, because our cells couldn't keep repairing the damage. But so that's obviously what happened with Marie Curie and all them that worked in this area. So polonium 214 is an isotope because we got that number there, so it'd be 214Po. And so we could take a look at it and say on the periodic table he's number 84. And so when you find him on the periodic table, then you start there, and then you know your electron, because we're not talking about him having a charge. And so if he doesn't have a charge, then he would just have the electrons as 84, and then we'd have to figure out the neutrons, right? And I'm just going to show you on this where 84 is. This is, of course, remember I told you this was a blurry version of this, but there it is, polonium. There it is, polonium. So he's number 84. So I would take my 214 and I'd subtract my 84 from it, and I would get what? 9, 10, 11, 30, 130. Did I do that right? 8, 9, 10, 11, yeah. Okay, so I would have 130, I think I did that right, my numbers are right, of the neutrons. And so with 130 neutrons, I'm way bigger than my 84 balancing out thing. So I'm pretty unstable, and I want to get rid of some of this. So when I get rid of some of this, if I go through the process of alpha decay, then I can lose some of this mass really quickly because I can get rid of 2 protons and 2 neutrons, right? And so let's say polonium 214 undergoes alpha decay. He's going to spit out this 2 neutrons, 2 protons, so he's going to be bringing down the number here. So how many protons? So if he spit out 2 protons, he's now coming down to 82. Okay, and then of course neutrons also, how many neutrons have lost, and so that would then bring me down to 128. Okay, so I've lost mass here. So I've lost 2 here and 2 here. And then the electrons, they're, I don't want to say massless, but they don't matter in the mass as much anyway, but nothing's lost there. And so in the end, now polonium 214 is now going to be down to the daughter product of 2 less of the protons, and that's where you get the name. So we'd have to go down to 82, and if you looked at 82, let me find it here, right there, it's lead. So polonium decayed into lead. And so now we're decaying this way, where uranium was actually going that way in that particular process. Just trying to get rid of some of the energy in the nucleus. And this is actually getting rid of some of the mass along with that energy, because all these guys have energy involved in them. So now lead is the daughter product, and we'd say we would have to put his number in BP or PB. Now before, we didn't change when we were looking at neptunium from uranium to neptunium. His number 239 did not change because he only ejected the electron. But now this one is actually ejecting something of mass. The protons and the neutrons are massive in the sense they have mass. And so 2 were lost here and 2 were lost here. So he's lost 4 of his mass. And so in the 4 of his mass now, he's going to have to be a different number, right? And so if we add this up, 8 plus 2 would be 10 and carry the 1, and then 8, 9, 10. And then we would have his number become 210. So 210, which is really just 4 less than this guy. So, which makes sense. He lost 2 here, he lost 2 there. And then you would have your end of the daughter product. And so that is the process of alpha decay. And then the last one is the gamma decay. And with the gamma decay, it's actually the most extreme, but it's the easiest to understand in the sense of we don't have to convert to who do you change into. That's the one good thing about gamma, though it's the most extreme and not good for our cells and such. All right, so gamma decay is when a radioisotope becomes stable by emitting a gamma ray, a high energy photon. Photon is the packet of energy. Like, just think of it as like, this little ball of energy that it puts in this little packet and throws out. And we talked about that in the electromagnetic force last chapter. So the gamma is going to spit that out, right? So like I said, it's the most extreme, but easiest to understand, because when it spits it out, all you're losing is energy from the nucleus. The amount, the level of the energy, it's not in the sense of a particular particle. It's not, okay, I'm just giving you an electron, or I'm just giving you a positive charge or a negative charge. I'm giving you like a big packet of a bunch of energy. And so this high energy packet is spit out, and therefore then the nucleus is less unstable, because he doesn't have so much energy going on in the packed density of his nucleus. Now, when this gamma happens, like I said, this is going to be a more dangerous side of the flying off. So what I did was put it in order here so you could see. If we want to say an atom is going through the alpha decay, you can stop the alpha decay as the atoms are flying, as the little helium nucleuses are flying off. Those can be stopped by a piece of paper or something very thin, like they won't penetrate your skin or whatever, if you have something blocking it or whatever, but for the most part. But then the beta decay is a little bit more, because this energy, see, when this alpha is coming off, it's coming off together kind of in a package deal. But with this is like actually just the negative charge, or the negative charge flying off. So negative energy hitting you. And that is said to be stopped by metal. So you would, if the atoms are going through a beta decay, you would want to have some protection, which we call shielding, when we put something in between us and the radioactivity to be able to shield our cells or whatever from it. Gamma would be problematic because you would need several inches of lead to stop the gamma ray that boosts off of that through that process of radioactive decay, or the gamma decay. So that would be more dangerous. So when we think of radioactivity, it's happening all the time, and atoms are decaying into other atoms, and these processes are sure and happening, but like I said, we have the mechanisms for our cells that are putting us to repair, recreate, all that good stuff. So unless we put ourselves in a situation where we're in the presence of a whole bunch of this stuff happening, decay of radioactive situation, like Chernobyl, when they had the nuclear power plant explosion, which I'm going to attach some information on the Google Classroom about radioactive decay. I want you to watch some videos, and it'll be just interesting for you to see. But the normal amount of radioactivity that you can be exposed to can be measured on a Geiger counter, I think is what they use, the Geiger counter. And you can have a certain amount, but you don't want to exceed a certain amount. And back in the day when the Chernobyl and the power plant explosion happened, the counters that they used only went to a certain level, because no one would ever be normally in the presence of way more than that. So like, I can't remember exactly what the level it was, but let's say their counter only went up to 5, and normally you would only have it'd only go up to 1 or 2 or something with your normal, or like 0.2 or something for normal amounts of radiation. And so maybe they made the device to go up to the number 5 or something, saying, well, just in case we have a big problem. Well, this thing will show us, you know, and it only went up to a certain number. So when the explosion happened, they were still using those tools that only went up to a certain number, and they were reporting to the government and the people that, oh, you haven't been exposed too much. Look, you're only exposed up to number 5 or whatever the number was. Well, that's because that's only as high as the tool went. That was not the truth of their exposure to these terrible terrible experiences of radiation. And so therefore so many people died or got radiation poisoning from being in those presence of that high levels. So as long as you're not in high levels, then your body can handle it and all that. But if you are going to be in high levels, you're going to be in trouble. And so this is why if we get an x-ray or something like that, we always have those shielded like coats we put on so that your body, and there's certain limitations to how many x-rays you can have a year and all that kind of stuff in medicine. That's because they want to shield you from any of this type of stuff that happens through these processes. Okay, so that's going to end the study of the weak force and the governing process, the radioactivity that the weak force partially governs. Okay, and then like I said, I'll add some of the videos, and then I'll also see there. I think there's one more lesson for this chapter that we'll have to do, and I think it's on maybe the radioisotope dating, maybe the dating methods for rocks and stuff like that, I think, and we'll do a separate video on that. Okay, I miss all you guys, and I'm hoping to see you soon.